to record these. Fail. If anyone wants to be responsible for reminding me to read lectures, feel free. Sorry, guys. Okay, so number of different solutions that you encounter all the time. Almost everything is a solution, really. Air is a gaseous solution. Okay, we can have solutions that are gases, liquids, and solids. So air is a gaseous solution, nitrogen, oxygen, argon, a lot of CO2, too much right now. Soda or pop, depending on where you're from, maybe Coke. Solution of gas and solids in water. Okay. Brass is actually a solid solution. So that means the copper and zinc are evenly arranged, evenly organized, homogeneously organized inside that metal. One of the things that we're going to need to be thinking about in terms of solutions is the solubility of various solutes in a solvent. So the solubility is the amount of substance that will dissolve in a given quantity of solvent at a given temperature. So typically we're going to see these units here. We're going to have grams of solute per 100 grams of water at a given temperature. Okay. This 100 grams of water is just sort of convention. If you look up solubility on a Google search, you may see solubility in terms of kilograms per liter or grams per liter, but you just have to watch these units. I believe for the most part, our textbook is using grams per 100 grams of water. Okay, so let's think about sugar water. So sucrose has a solubility of 211 grams per 100 grams of water at 25 degrees Celsius. So what happens if we try to dissolve more, 220 grams, for instance, in 100 grams of water? What do we get? We're going to have excess. We're going to have a little bit of sugar piled up at the bottom of our glass, right? And you can do this experiment at home if you have your little gram scale out at home, right? Coffee drinkers know what I'm talking about. So 220 grams of sugar is a lot of sugar. And compared to 100 grams of water, it's going to seem like an insane amount of sugar. It will eventually dissolve. Some of these things take a while to dissolve. So the rate at which it will dissolve does not correlate necessarily with the amount that will dissolve. Okay? So if you feel like trying this experiment at home, expect to be stirring for a long time. So here's just a little figure representing what you're going to see when you try to dissolve 200 grams of sucrose in 100 milliliters of water. You're going to end up with 9 grams of undissolved sucrose or sugar. And what we call this solution, there's a good term for you, is the saturated solution. Okay? So we've got the most amount of solute dissolved that we can get at a given temperature. Okay? If we were to heat up this solution of water and sugar, the way that sucrose works is we would actually be able to get more into solution. So if you ever have, maybe you try to sweeten your tea, you have iced tea and you try to dissolve sugar in it, it doesn't go in very well. If you have hot tea, it'll go in a little easier. Yes?
Do you have a glass of sugar water and you cooled it down when the water and sugar separate?
Yeah, very well could. So you asked if you had a glass of sugar water, let's say it's saturated, and you cool it down, would you be able to get a precipitate? And the answer is eventually yes. Depending on the curve for sucrose, I'm not sure what temperature that would occur at, but yeah, it would depend on that. It would crash out eventually. Yes?
Is there like a max amount of sugar once it's like super saturated where like you won't be able to add any more after you get to that point?
So that the max amount of sucrose or solute is given by the value in the solubility.
Okay.
So the other thing you mentioned, supersaturated.
Right.
So let's keep in mind that supersaturated is a whole different beast.
Right. I'm saying like once you get beyond the saturated solution and the supersaturated, is there a max amount of sugar that you can add to the solution before it will dissolve?
Okay, so the question is, we've dissolved as much sugar as we can. We're going to force it, probably by way of heating, to get a supersaturated solution. Is there a max at that point? Yeah. Yeah. The way that salt piles work, so our salt reserves for salting our streets in the winter, those are huge piles of salt, right? Why don't they dissolve when it rains? A lot of these piles are kept covered, but one of the reasons is because if they form a solution with the rainwater, they actually crash back out of solution because there's just so many crystals around it. Okay. Unsaturated means we have more room, okay, kind of a bad term, but more room to dissolve more solute. So we've got unsaturated, we've got saturated, and then there's some more definitions here. When we think about our saturated solution, okay, here's our dynamic equilibrium again, okay? In a saturated solution, so a solution where you've got maybe some solid at the bottom of the beaker that didn't get dissolved yet, and will not dissolve, okay? That solid and the solution are going to be in dynamic equilibrium. So that means that as some of the solid is dissolving, some is crashing back out and forming a precipitate. Well, what time do we have? I'm going to do a demo for you. Or, well, I don't have like an actual chemical demo. That'll be Monday. Stay tuned. I didn't check if this computer has Java, so this may not run at all. That is very loud. All right. This is called a Phet sim. Have you guys seen these before? I'll post a link to this too. You can access these. There's a website with a whole bunch of simulations that are pretty fun. So what I want you to do is watch this demo. I'll kind of describe what I'm doing. And I want you to write your observations in your notes. And then think about dynamic equilibrium. Let's pick silver arsenate. So silver arsenate is a slightly soluble salt. Okay. You guys remember your solubility rules? I'm sure you all remember them. Okay, so what I'm going to do is shake our shaker that is full of silver arsenate, and we're going to watch it dissolve. Okay, so again, keep track of your observations, write them in your notes. That was a few shakes. Let's see. How legible is it? So on the right-hand side, we're keeping track of the number of ions that are present. And we can actually change our volume of water if we want to. I'm going to add some more. Okay. Is it going to dissolve? Yep, looks like it's still going. Let's do some more. Okay. It looks like, if you take a look at, will this work? No, I don't have mine. If you take a look at the bottom in the middle of the beaker, looks like we might be starting to form precipitate. You'll notice that some of the ions don't look like they're moving very much. Let's add a little bit more, see what we get. All right, now we definitely have some solid forming at the bottom of our beaker. And what do you see with the ions? Let's just look at the solid part. It looks like some of those ions are sort of staying in place. Others are leaving, coming in, leaving, coming in, leaving. So that's our dynamic equilibrium. Okay. You'll notice that in general, the structure that's being formed is going to be, it's going to have a nice crystal structure. Okay, so you kind of keep an eye on that. There's different salts in here that form really cool. Yeah, this one's good. They form really cool structures. That one just made a big old pile. I think I dissolved too much. Yeah, but anyway, I could sit in there and play for a while. All right, so again, I'll post a link to this, and you can play with it too. Okay. Oh, that went back. Well, oh, okay, that was pretty seamless. Questions on that simulation? Okay, so here's a sort of reminder of what we saw in our simulation. And a very generally written equation that is going to be representing dynamic equilibrium in solutions. So we've got solute plus solvent, in this case water, in equilibrium with our solution. So this double arrow, you're going to see a lot of these. It means that we have the reaction occurring in the forward direction, and we have the reaction occurring in the reverse direction. So we have solute and solute combining to form a solution, and we have solution precipitating essentially and forming solute plus still solvent. It's kind of a weird, very general equation that's not great to just say, because you don't really form more solvent, right? But you do form that solute back again. So here's our supersaturated solution. We'll actually do this demo on Monday. I'm really excited, it's super fun. So basically a supersaturated solution contains more dissolved solute than a saturated solution. Okay? It's more in there than mathematically or experimentally shown to happen. And one of the ways that we make this happen is by heating the solution. So many cases, that increases the solubility for a given solute. Here's a great example. We talked about sucrose. The solubility at 25 degrees Celsius was 211 grams per 100 mils of water. At 100 degrees Celsius, it goes up to 487 grams per 100 grams of water. Okay. The ratio is crazy, right? This picture, this actually is a picture that I took a number of years ago. This is sodium acetate in the beaker, okay? And we're going to dissolve, this is 65 grams of sodium acetate. We're going to dissolve that in 15 milliliters of water. So I don't know if you can see that, but 15 milliliters of water is that amount. Right there, that tiny little amount. And you have to heat the solution to get it to dissolve, but it eventually does dissolve. And we'll play with this solution on Monday. This is a solubility curve for sodium acetate. Okay. On our y-axis, we have the solubility of sodium acetate in grams per 100 grams of water, 100 milliliters of water. And we have temperature on our x-axis. This pink line is going to represent, the saturation line. So, let's see, 25 degrees Celsius. And for the solubility of sodium acetate is about, what's that, 50, 60, 70, 80 some grams per 100 milliliters. Okay. What do we have in this sort of orange looking, that's very, very faint orange looking area? So we're going to have, what kind of solutions are we going to form? Supersaturated. And then below our saturation line, we're going to have unsaturated. Okay, I think the next slide actually says all of that. All right, skip that. Okay. So we've been talking about dissolving solids in water. This is just a fun little picture of dissolving a food dye in water. I don't know. I enjoy watching that happen. Okay. Put that in there. But why does it happen? Why do solutions form? Why isn't it that we put a drop of food dye in water and it just, sits there as a drop? Why does a solution form? And this is sort of the big idea in, I think it's section 3.1 in your textbook. Okay, why it is that solution formation happens. And what the textbook calls it is essentially a natural tendency to mix, which doesn't really tell you anything. It says that it's going to happen, but it doesn't really tell you why. This figure is showing that if we have two different gases, one diatomic with represented with blue spheres and the other represented with red spheres, separated in two round bottom flasks, if we allow them to mix, eventually we will have a homogeneous solution. Okay? Again, sort of similar thing. We have oxygen, a diatomic, and we have argon in green. And there's initially a barrier in place. We let that barrier go, allow the gases to mix, and we form a solution. Why? There's two reasons. Okay, one of them is something we're going to cover in a lot of detail in chapter, I believe it is 19. Yeah, it's either 18 or 19. But it is referred to as entropy. Okay. Oh, chapter 19 it says right there. So entropy is sort of referring to the spontaneity of something to happen. How spontaneous is the process? Does it occur without any sort of force behind it or any sort of heat behind it? And the mixing of gases is a spontaneous process. No input of energy is required. So entropy is one of the factors. Enthalpy, do you guys remember enthalpy? Yeah, a couple nods. Okay, that's chapter 5, I believe. Enthalpy, is referring to the amount of energy in terms of heat that is required to make a solution form, in this case. Why is that not important in terms of gases? So enthalpy does not factor in this example. So why is that? Anyone have a thought? Yeah?
Intermolecular forces are so weak between gases that they can disperse with particles.
Yeah, I said, and intermolecular forces are so weak between gases that the gases can intermix without having to break those forces. And that's exactly right. So there's no heat needed or some additional force needed in order to break apart the intermolecular forces in a gas, because essentially there essentially are no intermolecular forces in the gas. But that's not going to be the case for many of our solutions that we're going to talk about, especially our aqueous solutions. Okay. So the solution process is going to be sort of a three-step process. What we need to do overall is take a solute and distribute that through a solvent. make a solution, homogeneous mixture, okay? So what we're going to have to do, number one, is break apart any intermolecular forces in the solvent to make room for the solute to go in. Okay? The second thing we're going to have to do is separate the solute into its individual components and break those intermolecular forces. So those could be hydrogen bonding, they could be dipole forces, or London dispersion forces. Okay? Eventually, we're going to allow the solute and solvent to interact. So steps 1 and 2 are going to require energy. So we need to break apart forces. And in step 3, this is actually going to release energy. The magnitude of energy that's released is going to depend on the solute and solvent themselves. Okay. Yes?
So basically, the solution process is both endothermic and exothermic?
The solution process will have an overall either endothermic or exothermic properties, but the individual parts of breaking up the solute, breaking up the solvent, and allowing them to interact, they're going to have opposite.
Okay.
Okay. Here's just a figure sort of representing that. We're breaking apart our solvent, we're breaking apart our solute, and we're allowing them to mix. 1, 2, 3. All right. We'll start here next time. Have a great weekend.